We've been working with matrices and determinants. Today we're going to see how we can use applications, or the applications that we can use for this. The first one is called Cramer's rule, and don't write this down, okay? But we've got an equation, a system of equations with two variables, two unknowns, okay? Much like what we solved last chapter when we had two equations, two unknowns, and we used elimination, okay? And Cramer's rule says that if you strip off the coefficients and make a coefficients matrix, and then you want to evaluate that coefficients matrix as a determinant. Notice we have the absolute value type of symbols instead of the square brackets, okay? So we can find the determinant of the coefficient matrix by simply downward diagonal, upward diagonal, change the sign and add, okay? So that's called our determinant. Now, when we take that same determinant, but we replace our x column with the answers, we get our determinant with the x's switched out. Okay, and we do the same thing with the y's. Take the y column and replace it with the answers to our equation. That's the determinant with y's taken out. Okay, so they're using notation here. And again, don't copy all this down because you can always go back to your book to refer to it. Okay, I want you to sit tight and think. Okay, so for example, here's our system. 2x minus 5y equals 3. This is the part you can copy if you want. Okay? And negative 4x plus 3y equals 8. All right? Our coefficient matrix is going to be, strip off the variables, 2, negative 5, negative 4, and 3. So when we want to know the determinant of the coefficient matrix, we just remove those square brackets and write them with absolute value signs. Okay. When we want the determinant of, with the x's replaced, we take away the x column and put the answers there. 3 and 8. The y's stayed the same. And when we want the determinant with the y's removed, we leave the x's where they were, but we replace the y column with the answers. So far, so good? You see what we're doing, not necessarily why we're doing it. All right. So it turns out that x, using Cramer's rule, this is Cramer's rule, says that if you use your determinants with the x's taken out over the determinant of your coefficient matrix, you'll get your x. And if you use the determinant that has the y's replaced and divide it by the determinant of the coefficient matrix, you get your y. Okay? So let's see how that works. What is the determinant of our coefficient matrix? 6, right? And a 20, change the sign, add them up, we get negative 14. Okay? So that was our determinant of our coefficient matrix. Okay? Now let's find out what the determinant looks like when we have removed the x and replaced it. So 3 times 3, and 8 times negative 5, negative 40, change the sign, and add. So 49 is the determinant with the x's removed, replaced, and we had our determinant from the other. What is 49 over 14 going to reduce to? Yep, negative 7/2, negative 3.5. Doesn't matter how you write it. Okay? Let's find the determinant with the y's removed or replaced. 8 times 16, and negative 3 times, or 3 times negative 4. Positive 12 when we change the sign, we add them up and we get 28. So we put the 28 over the negative 14, and we get negative 2, right? So our answer to this system is negative 3.5, negative 2. So far, so good? Let's do another one. Okay. So use Cramer's rule to solve. System of two equations, two unknowns. This time we're not going to use elimination anymore, or substitution. We're using Cramer's rule. So x, bless you, is the determinant with the x's replaced over the determinant of the coefficient matrix. Okay, so we're going to replace the x's. What's going in my first column? And then the y's are just like they would be. And what's my coefficient matrix? And the y will be equal to my y matrix with the y's removed. So what goes in my first column? And what goes in my second column? And then we write out our coefficient matrix. All right, evaluate those matrices for me, or those determinants for me. So I close the door and remove distractions. (24 minus 13 gets us 11. And we know this will be a negative 11 again, right? There's no need to evaluate it. It's the same determinant on the bottom, the denominator. So 8 and 13 times 4. Change the sign. Negative 52 and a positive 8 gets us 'So my answer So what do you think? Easier than solving systems of equations the old way? Faster probably, right? And so this is something that you can use on an ACT, a PSAT, and SAT to help solve systems quickly. Make sense? All right, let's try it with a 3 by 3. And any questions on this one? All right, we're going to do this one with a 3 by 3. Hopefully it's just as quick and easy and painless. So there's your 3 by 3. System of 3 equations with 3 unknowns. With these, rather than rewrite the determinant of our coefficient matrix over and over and over again, I often will just say, hey, let's find the determinant of that coefficient matrix right away. And just know that that will be our denominator for all 3 variables. Everybody okay with me using the diagonal method? We can always expand by minors, probably row 3 or column 2, but for some reason I think this is faster and less error prone. Downward diagonal, we get (84). Negative times negative is positive, so 3 times 2. And we'll get a 0. So we've got 90 in the bottom. Upward diagonals, multiply, change the sign. So 2 times 4 is 8, times 2 is 16, change the sign. 0 times 3 times negative 3. And then 7 times negative 1 times negative 1 is going to be a positive 7, so change the sign, negative 7. So 90 minus 23 is 67. So no need to rewrite it over and over and over again. Okay? To find x, we're going to use that determinant with the x column removed and replaced over 67. To find y, same idea, over 67. And to find z, okay? So we're replacing our first column with 18, 1, negative 5. Second column with that, and third column with that for y and z. So far, so good? All right, then again, you can expand by minors, or you can simply rewrite the first two columns and then use the diagonal method. 18 times 4 times 7. (504). Negative 1 times negative 3 times 5 is going to get us a positive 15. And then the last one will get us a 0. Upward diagonal, negative 5 times 4 is a negative 20, times 2 is a negative 40. Change the sign. 0 times negative 3 times 18 is 0. And 7 times 1 times negative 1 is negative 7. Change the sign. So 504 plus 15. Plus 15 minus should be plus 15. Did I copy that right? Should be a negative 5. I didn't copy that right. So 504 minus 15 plus 40 plus 7 gets us 536 divided by 67. We know our x coordinates value is 8. Okay. Same idea with y. Rewrite your first two columns. Downward diagonal 21. Downward diagonal 8 times a negative 18 times a negative 6. And 2 times negative 1 times 5. Negative 5 is going to get us a positive 10. Upward diagonal, 2 times 1 times 2 is 4. Change the sign. Negative 5 times negative 3 gives me a positive 15, times 3 is 45. Change the sign. And 7 times negative 1 is 7. Negative 7 times 18 is a negative 126. Change the sign. So negative 4 and negative 45 is negative 49. Add that to 126. Add 21, subtract 108, add 10. What do you get? 0. Okay, these are tough numbers. All right, next one, last one, z. We're rewriting 3, -1, 2, -1, and 0. Downward diagonal will have a -60. Then -1 times 1 times 2 will be a -2. And the third downward diagonal gets us a 0. Upward diagonal, 36 times 4, 144. Change the sign. Then 0 times 1 times 3 is 0, and -5 times -1 times -1 will be a -5. Change the sign. So a -144 plus 5 minus 60 minus 2. We get 3. Okay, these were tougher because that determinant was a big number. But I showed you a tougher one. The homework assignment should be lighter, easier. Questions on this one? We'll get very good at evaluating determinants. Lots of practice. Which one? For Z? It should be, it's positive 67. We had a -144. Yes, it should be a negative, shouldn't it? Because a negative, yes, I'm sorry, -3. Good catch. Lost my sign. Other questions on this one? All right, so other applications, okay? Jury may be out. Is this easier than solving a 3 by 3 the other way? Maybe, maybe not, right? Especially when you have a nicer numbers, right? Okay, but this is Cramer's rule, and this is another way of finding the solution to a system of 3 equations with 3 unknowns. Okay, so here's another application of matrices, determinants. Don't write this out, okay? Just the problem. Okay? The idea behind this is that you can find the area of a triangle when you're given 3 points, 3 coordinates. And you do that by writing the ordered pairs as first column, second column. X is in the first column, Y is in the second. And you fill in the third column with ones. And then you evaluate that determinant and then multiply it by either a positive 1/2 or a negative 1/2, depending on whether your determinant is positive or negative. Because we always want our area to be a positive value. Okay, now think of how hard this one would be to do otherwise. You'd have to graph these points, right? Then you'd have to find the length of the base, and you'd have to find the altitude, the height, and find that value using distance formula. We're a perpendicular height to the base. Okay, but it's much, much simpler using determinants. So we have the 3 points, 1, 1, 2, 3, and 3, 2. So we simply write them down. And then we fill our third column with ones. And we're going to evaluate that determinant and then multiply it by either a positive 1/2 or a negative 1/2, depending on whether this answer was positive or negative. So far, so good? And again, you can always expand by minors, but I think it's faster just to say 1, 2, 3, 1, 2. You can put the 3 there if you want to. It won't be used. Recopy your first 2 columns. And downward diagonal, downward diagonal, downward diagonal, upward diagonal. Change the sign. Multiply upward, change the sign, multiply upward, change the sign. So a -13 and a positive 10 gets us negative 3, right? So negative 3 is almost our answer, but we need to take that times negative 1/2. So 1.5 square units. I think you can agree that this is much easier than trying to find the area of a triangle by plotting it, finding the base, finding the height, using distance formula. Okay. All right, next one. Another application of determinants. And again, we're not going to write all this out, okay, because you can refer back to your book. But it says that if we have 3 points and we want to know if they are collinear, they're all in the same line, okay, then we simply write down the 3 ordered pairs and fill the last column with 1s, and then we check and see if that determinant is equal to 0, then we know we have 3 collinear points. If it's equal to any other number, they're not collinear. Okay. So we'll rewrite. We have the point 3, negative 1, 0, negative 3, and 9, 3. Fill the last column with 1s. And we want to know, is that going to be equal to 0? So far, so good? All right, rewrite our columns. Downward multiplication, negative 9, negative 9 again, and a 0 upward, and change the sign. Positive 27 when we change the sign, right? Negative 9 and a 0. So 27 minus 9 minus 9 minus 9, is that equal to 0? Yes. Is that easier than plotting 3 points and figuring out if they're collinear or not? Collinear means they have to have the same slope, right? And they all have to go through the same point. Okay? All right. Last example. Last application of matrices. Except for decoding, and I'll know that we'll do that. Find an equation of a line passing through 2 points. Now this one, you decide. Jury's out whether this one's easier or not using determinants. But the idea behind this one is that if we have 2 points and we want to find the equation of the line, you simply write x and y as your first 2 values, first row, first column, second column. Then you write your other 2 coordinates, and you fill your column with 1s, and you set it equal to 0. Okay, so it will look like this. Oops, got to put my x and y up here first. Fill your last one with 0s. Okay, we want that to be equal to 0. I'm going to put it over here so we have room for our 2 column addition. So we rewrite. And then we multiply. Downward diagonal. Negative x, right? Downward diagonal. 3y. Downward diagonal. Upward diagonals change the sign. So positive 3, right? And then a negative 5x when we change the sign, and a positive 3y when we change the sign. So I have a negative 5x and a negative x for a total of a positive 3y and a positive 3y. negative 15 and a positive 3 has to be equal to 0. That is an equation of the line. Okay? Our book would say, hey, there's a 6 in common with everybody. Let's divide everybody by 6. So negative x plus y minus 2 equals 0. You could get it into slope-intercept form and everything else, but you can stop there as far as I'm concerned. Okay? That's an equation of a line passing through those 2 points. Okay? Questions on this one? All right, feeling good? 4 applications of determinants. Cramer's rule to solve systems, area of a triangle, how to determine whether lines are 3 points are collinear, and how to determine the equation of a line passing through 2 points. All right, so there's your assignment.